All right, so I'm going to be answering more questions more often. I'm going to try to do one question a day as we head towards Christmas. So if you do have any questions as we head towards winter break this final last couple of weeks, I'm going to try to do a video a day. If you do have any questions, send them to me, questions@bothellstemcoach.com. I'd be happy to take a look at it if I have time. So ask me more questions. I'm going to try to do as many as I can. I'm going to aim for one a day, okay, for a while. So we have a block mass M, slides without friction along the loop track is shown. If the block is to remain on the track even at the top of the circle, whose radius is r, what minimum height must be released? So this is a work and energy problem. Okay, it's combined with a little bit of circular motion here. So you might be like, this is a lot of information here. So when we're doing work and energy, the first step we always want to think about, this is what I always have my students always think about, what's the first thing we want to do in a work and energy problem, is to think about, okay, what is the system? Identify this system. Now, whenever we are changing height, we're going to use the earth. So it's going to be the block plus the earth. Then you want to draw a free body diagram. Okay? Just like drawing a free body diagram. I'm a broken record on this. Sometimes you got to draw a free body diagram during the motion. What's happening is there's some gravity acting on here. There's some normal force. And then there's no friction. So there's nothing else happening. Now, keep in mind, the normal force and the gravity will change during the motion. Like down here, right, the mg is going to be downward, and the normal force is going to be like more like that. So it's going to change, but overall get a representative picture. 3, compute or set up an expression for work. So some rules about work here. Work is the force has to be parallel to the displacement. Okay, that's one thing for work, and that's what you're going to compute. And then if the force is perpendicular to the displacement, it doesn't do any work. So the reason we did this setup is we want to think about what is the displacement. Well, at any moment in time, the displacement is parallel to the ramp. That's the direction of the motion. So the normal force is actually not going to do any work because it's perpendicular to the normal force. So by being perpendicular to the normal force, it doesn't do any work. The work done by there is 0. Now, gravity technically would do work, but because we've made the system the block plus the earth, we account for the work done by gravity as part of the potential energy. So the mg is not going to do any work. So what we found at this point is that the work is 0. Work's not always 0, but in this problem, work is 0 because there's no friction. If there were friction, then we'd have to consider work done by friction. 4, then we want an expression for the initial energy. The initial energy, and that's where we're like dropping it from. So here we're going to release it from rest, okay? We're going to release it, which means the velocity is 0. So at this point, so you always want to think about what forms of energy are we including? Because we have the block, we include some kinetic energy. Because we have the earth, also we include gravitational potential energy. So our general expression is there's some kinetic energy plus some gravitational potential energy. Now, because the V is 0, this is the initial, this is the start, right? There is no kinetic energy. And for gravitational potential energy, you do have to set a reference height. We'll set the reference height as the very ground. It's not always the ground, but like this is h equals 0. So the height above this point is h, so the initial energy is mgh. 5, we now want an expression for the final energy. Okay? So what is the energy? Now, what do we care about? We want, even at the top of the circle, we want to remain contact. So we're going to talk about this point here. All right? So at this point up here, we want to think about what energies. Because if we're going to lose contact with the track, it's going to be up here. Right? Like, over down here, like, if this thing is not going to go fast enough, it's definitely going to happen at the very top here. So let's think about what forms of energy we have there. Again, we have some kinetic energy and plus some gravitational potential energy. Now, we don't know how fast it's going, so we'll just leave that alone. Then we have mg. What's the height? Well, the radius is r. From there to there is r. And so compared to the ground, the height is 2r above the ground. So we put 2r here. Okay, so this is 1/2 mv squared plus 2 mgr. And last, we apply the expression work is the change in energy. Final energy minus the initial energy. Okay, so work causes a change in energy. So our work was 0. Our final energy was 1/2 mv squared plus 2 mgr. And the initial energy was mgh. Okay, so this is our equation. Now, sometimes when the work is 0, we say it's conservation of energy. The final is going to equal the initial, so you could set these equal to each other. But I really just took our final energy minus our initial energy and set it equal to 0. Now, at this point, I don't know V. Like M, G, and R are kind of like assumed to be given pieces of information, right? Like they gave us there. But we don't know the V, so we have a little bit of a problem here. We need to know the V in order to solve for the H. Like the V is unknown, so I can't solve for H because it would depend on the V squared part. So then we have to talk about, well, what would it take to lose track, right? And if you're understanding about losing track with it, we're going to draw a free body diagram up here. So if we were to draw a free body diagram, you'd say, well, I have gravity. So we're going to do kind of a forces analysis and then think about it. And then because the surface is above it, you'd have a normal force up here, above it, like that. And those are all the forces acting on it. Okay, so now we're doing a forces kind of scenario. We drew the free body diagram. Because there's not a lot of things you can do in physics. At this point, if you guys aren't working energy, you either have set up your kinematic equations, you're going to draw a free body diagram, or you're going to set up a work and energy equation. It's like really only 3 things you can actually do at this point. if you're not sure like why you're going to do this. Okay, draw the free body diagram. Identify the acceleration. This is the next step, right? What's the acceleration? Well, it's moving in a circular path. If it doesn't lose track, the acceleration is downward towards the center of the circle, and it's centripetal acceleration. Okay, so then now we apply F net equals ma. What are the sum of the forces? It's going to be mg plus Fn equals mv squared over r. Because the A is centripetal acceleration, and centripetal acceleration equals v squared over r. So you notice that, like, hey, there's some kind of v squared here might be helpful to figure out. But let's take a look at this expression. Now, we want the minimum height. So obviously, we can always make it, if I do it super high, it's going to make it all the way around. But the minimum height, if I'm about to lose contact with it, I'm about to lose contact. Like I have to remain contact because we want to remain contact on the track. So we want it to barely touch it right here. We want the Fn to be almost 0. Not that it quite lost track. Lost track would be definitely 0. But very close to 0. Right when it's about to lose contact. Kind of like when I touch the wall right behind me here. Okay, very gently. The normal force is very small. I'm touching it, but there's a small normal force. So very, very close to 0 is right when we would do that. So then when we get rid of the Fn, then the m's cancel. Look, the v squared equals gr. And that helps us because now we can take that and plug that into there. And now I can solve for the h. I can move the mgh over here. Equals 1/2 mgr plus 2 mgr is 2.5 or 5/2 mgr. M's cancel, G's cancel. The h is going to be 5/2 r. Okay. I hope you guys see, this is the process. This is my work and energy process. I'm always going to do this process for work and energy. I'm always going to do this process for free body diagrams and forces. That's kind of like the process. Those are the steps that I'm going to use every single time. You guys have any more questions? Hit me up and let me know, okay?